Hey guys, what's up? Eddie Alho here with KissAnalog.com. So today, I think it's pretty exciting because I found a tool that you might all like. It's a math tool, and I thought I would use it for doing this design that we're working on, this PFC design, which we're going to do the second converter very soon. And so, you know what? Showing you the math and going through it. And what's really neat about this kind of thing is you can save it for one project, change some variables, and use it again for another project. It just kind of helps you see all your math in one place. It's like a scratch pad. You can see your equation. You can see, oh, if I change this term, it's in the denominator, the numerator. If I change it, it's going to make a big, the response, the answer bigger or smaller. So I think it's just a cool way to do it versus Excel, where the equations are kind of hidden in a cell until you go click on it. Then it shows you the equation. And even that might not be as simple and easy to read as something like this. So if you use MathCAD, you're going to be familiar with a tool like this. And I was going to use MathCAD, but I found this tool, just stumbled on it. So I just wanted to share it with you. So let's jump in and let me show you this tool. And it's free, guys. It's free, simple, and easy. So at least that's the way it seems to me. So let's just jump in and let me show you this tool.
Alright guys, so if you go to Blockpad .net, you'll see this. And you can make an account really quickly and easy. And look at this, trust by engineers. Wow, I'm an engineer. I trust it already. Anyway, here's some of the interesting things I'll show you. Blockpad, easy format. Excel kind of has a few check marks. MathCAD, a tool that I have always liked, has some check marks, but look at this. Blockpad has all these check marks. I'm glad I found this because this does seem like really cool software. So look, download for free, quick start guides, sketches. I'm gonna have to learn how to use this thing so I can teach you guys a little bit more about this, right? Show you on the web page. But anyway, I just want to show you their web page, and all I did is say get started, and I just said new document. I just started without even getting an account, but now I have an account, and there's my account, and that's kind of what my front sheet looks like. So I can open up a new document. I can do any one of these things here, and look, here is the program I have. If I double clicked on that, it would come up with this. So here is my spreadsheet, 400 watt. Maybe I should put my name on here, huh? So here, let's click on this and go Kiss Analog. There we go. 400 watt PFC converter. Pretty cool. And then from here you can see this says heading 1. So that's what that is. And this is some kind of multi-font family, and font size is 10. See, if I come down and click on this thing, it shows paragraph. If I click on this input one, it shows heading 3. That's what I use for most of these headings, by the way. Then here's all these equations. Pretty cool. All you have to do is, let's say if I wanted one of these things for, say I got a micro, nano, kilo, mega, milli. How about a mega, capital M? And then equals 10. And I hit the up arrow above my 6 key, and whoops, and 6. And then hit return, and it just shows. There it is right there. And then look, here is this thing. It put part of it over here because I was at the end of the line. So if I go up here, put my cursor there and hit return, it'll drop it down to the next thing. And then if I click on this, I go to this value format right here. Click on that, and it shows me all these options. And over here, by the way, on the left, I'm on number. Okay. So I just come down here and I go, oh, let's use scientific, but I want engineering. The difference is this is a power notation, but it can give you like powers of the 5th instead of just multiples of 3, which engineering notation does. So come down here and you can see there's 1 meg. And you can see how these other ones, look, this one, I didn't do it. Let's try it there. Let's go 1000. I'll scroll down here, hit scientific, choose engineering, and there we go. So 1K, everything's in multiples of 3. That's what engineering does. This one I haven't done either, so I could do the milli one, but here's my inputs to this thing. 120 volts nominal. The minimum's 85, max 264 volts AC. V out is 400. Efficiency for the my next stage. See what I'm doing here is I'm saying that the next stage is going to be about 93%, I'm guessing. So on this stage, I want to put out, see right here, P out, this divided by efficiency is 430 watts. So if this stage puts out 430 watts, now obviously in this stage, if it's also say 93, I'll burn another 30 something watts, so it'd be 460 watts at the input. But the output power is 430, so my next stage, even with efficiency losses, I'll still have 400 watts. Okay, that's why I did that. And then I out, well, see when I double click on it, it shows me the equation right here. I out equals this, kind of small, equals that. Now if I just hit enter, it just closes it. So this stuff here on the color to the left, which is, I don't know what that is, kind of a greenish color, I guess. And then over here is kind of pinkish. That's the response, the answer to the equation I wrote. And it automatically does that for me, so it's really cool. And so here's the input RMS, 5 amps. The peak of that is square root of 2 times, so it's 7 amps. Bridge rectifier, you can see the numbers here. Okay, and then what I did is I calculated thermal. So I wanted to see how much thermal impedance do I need for my heatsink to cool this rectifier because of this 10 watts. And we'll go through this design stuff in another video. This one I'm just kind of showing you the equations I have. Power, the MOSFET. Okay, this down here, I gotta change this to MOSFET because I left it, I cut and pasted this, but I gotta change it to MOS for MOSFET. Okay, so there we go. And then this power bridge right here, I really want this right here, power dissipations on the switch. And then I have power dissipation on MOSFET where I put them both together. So I really want this one to finish this equation. So what I do is come over here and power DISS underscore ON. So what I do is when you hit underscore, it puts it down here as a superscript, or is that subscript and the superscript's on top? So anyway, it puts it down here. And then now here's a very interesting thing. You notice when I changed it here, look what happened. It changed it down here too. So wherever it finds, I think that's kind of neat, but at the same time, you could have that same term used somewhere else where you don't want it changed. And so that could be a negative kind of thing. Now, over here in the left corner, you can see this little block popping up saying, oh, dynamic equation, double click to edit. So it's kind of giving you little tips what to do. So now I think I got this back to MOSFET stuff. And so there we go. There's the MOSFET stuff. And here's boost diode. So you can see I did the same stuff for the boost. The inductor, that's how I calculated the inductor. Okay, now we kind of covered a lot of this stuff, so that's why I'm kind of glimmering by it. But now see out, again, I'm going to do another video where I go through all this stuff. Not real slow, but I'll pace through each one of them to show you. But see out, I'll just kind of cover that real quickly here. I got 3 different equations for how much capacitance I need in the output. This first one's based on the frequency, the line frequency. That's why I call it frequency L, and it's 60 hertz here in the States. So I'm going to go 2 times 60. That's where this 2 times 60 comes from, right here in the middle, because really we got 2 bumps, right? Because we're taking the negative bump, putting it up. So we're charging the cap twice the frequency. So that's that. So it's 2 pi, it would have been FC. See, if I put the C down here, swap C, put the V ripple up there, so you can just cross multiply and get them that way. If I did that, 1 over 2 pi FC is the X of C, right? So that's where that part of the equation comes from. But then we cross multiply and get V ripple down here, because we're trying to solve for the output capacitor. V ripple, we're saying is 10 volts over here on the left. Okay. Otherwise, it would have been, 1 over X of C, or it would have been X of C, right? 1 over 2 pi FC. Now on the top is I out. So if you go X of C times I out, that's your voltage. That's the voltage ripple. So you can see how you divide those across, voltage ripple would be equal to I out times X of C. So that's where this equation comes from. And solving for the C out, cross multiplying these, we get 142 microfarads. So at least 142 to maintain that. But here's another way to calculate that, is we want to hold up in between pulses, right? We're getting pulses every 120 hertz. So, but what if we want to hold up, so every 120 hertz is about 8 milliseconds. So what if we want to hold up for several cycles, say 20 milliseconds? So we go hold up is 20 milliseconds, 0.02, and we do this equation. And this is, the energy of a capacitor is 1/2 CV squared. So see this too, 1/2 CV squared. So power out, if you cross multiplied here, you'd get C out divided by 2. That's 1/2 of C. 1/2 CV squared. So see that here's a V squared. You multiply up here, you get 1/2 CV squared is equal to your, and that's energy. And then times time is power. That's just 20 milliseconds. So that's where this equation is derived from. I can walk through that equation also, but that would give us 270 microfarads. But now look at this equation, this third one. I'm getting double that capacitance. And what this is transient. These two things up above are about the input voltage and output current, maintaining that. The RMS, I out for 400 watts. If I want to do that, then these two things hold, okay? But what if I want to consider, what if I have a transient? I'm at 0. So the way I'm doing this is I equals C dV dt. And I can show you how this equation is that. And what I do is I manipulate it to get the C out. So C is equal to I times dt divided by dV. And so I'm saying that voltage can drop 100 volts at the input because the next stage can regulate through that. And it's similar to this one here in the middle. V out minus 310. So I'm letting the voltage drop 90 volts to get this equation. That's how that is. So the V squared is where you start minus where you could drop down to, and that's this hold up, okay? This one down here at the bottom, I'm just saying I'm going to drop 100 volts, so even a little bit more in this because the next stage can regulate through that, so that's okay. And I'm going to go from 0 to max I out, which is about 1 amp. And the transient is going to be 1 over 20 hertz. So maybe I have a 20 hertz note, right? And it's going to drop the power. Now, if I have a bunch of 20 hertz things, that's okay because they're going to be averaged over and you're going to be taking care about one big old gigantic 20 hertz thump. And I don't want to, interrupt that. So I want my second stage to ride through that. So I need a capacitor of about 527 microfarad. Now, this is really a worst case, guys, because I'm saying it can drop 100. Maybe it can drop even a little bit more. And also maybe you're not going from 0 amps to max amps, right? Probably not. So this value here is 500 something microfarads, is really a worst case. But between these three equations, you can see how you can cover all cases of transients, whether it's input voltage or output transients. So if we're around 500 microfarads or above, then we should be solid, okay? Now here's our shunt resistor. We sense the current going through the shunt resistance, and that's how we calculate that. It's the chip wants to look for a 1 volt peak, and so we go this 1 volt divided by the peak of the current going through the inductor. That's the value we want for that, okay? And we probably want to allow like for 20% of current above the max. So we'll choose something maybe closer to 100 milliohms, or we can go 20 times, we can add that so we can get it mathematically. Again, we're going to go through the design in another video. I'm just showing you the software. But I'm just showing you how I use the software. Now see, here's this guy. I'm trying to calculate resistors for the voltage set. So the bottom resistor is going to be 10K, and I solve for the top resistor, and that's 1.3 meg. But I really want to use several resistors because of the voltage stress on that input, that 400 volts. So I'm going to divide it by 3 and come up with this value. But now again, come up here to the value format, scroll down here at the bottom, scientific notation, engineering notation, say OK, and there we go, 441K, right? Pretty cool software. I mean, I've used MathCAD. Now these three equations down here are just kind of garbage. Let me get rid of those. Just kind of see how I just, I held the mouse down, highlighted them all, hit the delete. So I've used MathCAD for a lot of years, and maybe that helps me with this software, but it's, it's pretty intuitive. I need to learn how to use all these things, like what is a block. Obviously, we know what a chart is, and we can do a 2D drawing. So you can do some drawings and other things to show what you're trying to calculate. I could insert a picture of the circuit that I'm trying to calculate. That helps too. So this is a nice notepad, and you can extend it to pictures of the schematic and stuff like that, so you can see what you're calculating for each stage. So pretty neat software. Much easier than Excel because you can actually see the equations. As you scroll through, you can see, oh, if I make this bigger, then this gets smaller. If I change one of these things up here, bigger makes this bigger, smaller makes this smaller. So you can kind of see how your variables, or the parts of the the equation, changes the response, the answer to the equation. And I really like that, because sometimes you're taking trade-offs. You're going, well, I can make this higher up here, and then I'll make this bigger, or I make this lower, and I'll make that bigger, or this higher, So you can kind of see how the different inputs to your equation are affecting your output. Versus Excel, it's just hidden into a cell. You have to actually click on each cell to read what the equation is. So, and up here at the top, I'm just defining these terms so I can use them later. So if I want to say milli or K, I can do that. And yeah, and you can see how I type this in. There's times and times. And if I use the K values or the millis, I have to use times. I have to multiply that, that, here you go, 20 nano. So I go 20 times nano is that. So pretty cool, huh? And you cut and paste, do all those things. And I'll show you this software more if you guys like it. I think I'm going to try it out for a little bit more. I think I'm going to like it. So far, I really do like it.
Hey guys, so what do you think of Blockpad? It looks pretty easy. I mean, I just started using it today. It is very simple, intuitive. I have used MathCAD. Let me know what you guys have used in the comments down below. Do you use MathCAD, Excel? Have you seen Blockpad before? Do you know anything about it? I'm brand new to it, so I just wanted to do a quick video and show you guys this program, because I think through this design process I'm going to use that, because that's something that's free and I can share files too. So what do you guys think? Thumbs up? If you don't like the program, don't give me a thumbs down unless you don't like the video. Some people, when I review things, they'll give a thumbs up, thumbs down to the product, but that's not really what that thumbs up thing's for. That's whether you like the video. And by the way, give the video a thumbs up if you did like it, if it was useful. And 2 thumbs up to my patrons. You become a patron. There's a link down below. There's also a thank you button that a few people have used. It's super cool. Buy me a cup of coffee or something. It's a one-time thing. Just hit the thank you button. But if everybody could hit the thumbs up button or the like button, that'd be awesome. It's a free way to help support the channel, as well as all the links down below, you know, to Amazon and eBay and that kind of thing. So yeah, it doesn't cost you anything extra and helps support the channel. So I just wanted to show you that free software, because it's something that I can use for this design that we're doing, and I might continue using it. I was going to show you how you could download MathCAD and use that for free, but this one just seems so simple and easy. It is line based, so you write equations line by line, or spaces line by line, where MathCAD is more like a scratch pad. You can go anywhere on the page and just click and start writing an equation. Sometimes that can cause you problems if you're not aware of some things, like if you define a volts equal to 10 up here and you use volts down here, that works. If volts is above where you defined it, then it doesn't. So keeping it line based forces you to do it correctly, I guess, in the right order. The other thing, I think, because of the line based programming, when I change a variable, say if I go volts out DC and I want to just change it to volts out, when I change it, it changes it in all the equations below, which is super cool. I don't have to go click on every equation like I would in MathCAD and change that variable. Now, on the other hand, if you didn't want it to change all of them, well, that might not be super cool. So, and there's probably something in the preferences or in the options or something that allows you to change that. I'm brand new to the program. Seems easy to use, get up and running with it. Let me know what you guys think. As I learn things, I can show you, and if you're interested in that. But it'd be really cool to hear if people use MathCAD or Excel or Maple or some other program. And I could teach you guys Maple too as I learn it, because I do have a copy of Maple. Let me know what you guys think of that. But 2 thumbs up for watching the video, and we'll see you next time. And hopefully this will help you do your work. So we'll see you next time, guys. Thanks.